Recurrence relations happen a lot when you have powers of x, high powers of x in the integrand, but they also happen a lot with trig functions. So I'm going to get you to try one yourself. The example I'd like you to have a go at is this. Just before you do, I try it out, just in case the trig one is quite a lot harder, which is why I did this one first and I left trig until afterwards. But just in case you can't see, I mean, integration by parts, we're looking for a product, right? Looking for a product. So for instance, whenever it's hard to see an abstract, unknown value, stick in a constant, right? So if I were to ask you to do this, and I told you, okay, let's do this by parts, right? Clearly you need to break this up into a product of some kind, right? But you don't have many options as to what the product is going to be. You've got sine times sine times sine, so what might be a useful product? Probably sine and sine squared. Okay? There's not really other alternatives. If we broke it up to 1 and sine cubed, you're doing the same question. If you did sine squared and sine, it's the same thing. You could break that up into 1 minus cos squared, I think, but it wouldn't make anything easier because you've still got the same power of a trig function. Okay? So, that's how it would look with a 3. What would it look like with an n? Just to save you some pain and learning. It's good. It's good. It is good. But I'd be the I think something. Yeah, you are.
Are you going? I'm not going to anyway.
Should we give this a go? I've seen quite a few of you who've gotten it right. Well done. If you're struggling a little bit, that's okay. Recurrence relations are hard, all right? In some ways, and some of you have noticed this already, these are kind of the hardest thing within the integration topic. They can really bend your brain around. Let's have a go, shall we? Here's my IM, okay? So I'm going to rephrase that just like I did here as a product, and then I can choose my u and my dv, and then off I go, okay? So I'm going to write this as the integral of sine. Now, if I've got sine on as one factor, right, how many sines do I have left? N minus 1, right? So I'll have sine n minus 1 x there, okay? Now you have to be very cautious. You've got chain rule happening here. It's a bit easy to forget because you don't know what the power of sine is, but stick with it, okay? So I'm going to select my u and my dv now. Okay. So here's my grid, right? What are some wise choices? If we're going to be differentiating this thing, right, we want it to be the one which is going to make things a bit easier for us, and the problem's going to get simpler, okay? So which ought I to choose? Maybe I should phrase it the other way. I'm going to be integrating this one, right? So I want something that when I get over here, it doesn't make things worse for me, right? Probably integrating this is going to be more of a hassle, right? So that's why I'm going to choose this as u, okay? Sine n minus 1 x, okay? Now, because it's chain rule, you have to do two things. You've got to do the outside and you've got to do the inside, right? So I'll do the inside. It's just sine, isn't it? It's a bit hard to see because there's no brackets or anything, but the derivative of sine is cos, good. Then you do the outside, so the power comes down. I suppose since it's a constant coefficient, I'll slap it out the front, and the power reduces by 1. Now some of you are thrown at this. You think, have I done something wrong? Now that's a fair thought to have, okay? However, just consider the alternative. Suppose if I had put this here, would it not be measurably worse if I did that and then had to integrate, okay? So it doesn't look like it's ideal, but let me see if I can work with it, all right? What's my dv on dx? It's sine, okay? So that gives me a v of negative cos, right? Okay, good. I've made all my selections. I've put my pieces together. Let's integrate, right? I'm going to get uv. So that gives me this, negative cos sine to that power. Okay, and then I'm going across here, right? Now this does look quite bad. You're going, well there's a double negative, isn't there? So I'm going to go plus. That n minus 1 is just a constant, so I'll slap that out the front. And then what you have inside the integrand, right, is cos squared sine n minus 2, why did I put that bracket there? Sine n minus 2x with respect to x. And that looks like an awful mess, okay? But it's not as bad as it looks, right? Because cos squared, of course, we know lots about cos squared, and we can interchange it for something a lot more useful to us, right? Namely, 1 minus sine squared, right? So keep this guy out the front here. Plus n minus 1 lots of. Okay, now if this is 1 minus sine squared, I'm going to do the expansion in one go, okay? Your Z1, you can handle it. So I've got one lot of this, which will be this. Okay, minus sine squared lots of this. Okay, when you've got sine squared and you've got sine n minus 2x, what happens to the powers? The powers will add, right? That plus 2 and that n minus 2 will exactly cancel, right? So you'll get this. Okay, right. Now at this point, because we're trying to work toward a recurrence relationship, right? Because I can now see that these are in the form of one kind of I, right? I can start to make some substitutions here, right? This guy out the front, he's kind of, well, he's already integrated, so we don't need to worry about him, okay? But I have n minus 1 lots of, okay, 2 halves of the integral. What's this in terms of I? This is I n minus 2, isn't it? That's it. Now I could do brackets again, here, and have my in here, as you can see. But it's in my interest to actually stick that out over here separately because I want to make in the subject, right? So I'm going to have to kick him over the other side eventually. I might as well get him out of the brackets now. Okay. So I've got one in over there. I've got n minus 1. Wait, hold on. That should be a minus sign, shouldn't it? Yes? No one picked it up. Lazy. When I add this to both sides, okay, I'm going to add n minus 1 in's. Boy, that sounds confusing. N minus 1 lots of them over to the other side, okay? This negative 1 will cancel with this one, right? So I'll just be left with n of in. Okay? And I'm almost finished now. I'll just tidy up. That should be an n plus this. Okay, I just want in on its own, so I'll divide through. I suppose you could draw an enormous fraction line, but most people don't because it's long and awkward and you don't need to. So I'm just going to slap that there. And here I'm going to have n minus 1 on n. All right. So, does that look good? Does it make sense? Is it coherent? I think so. Looks right, as long as you've differentiated everything properly. It does look a little unusual because when you're going from in, you skip one. In the previous example we looked at, you got in minus 1. That sort of made sense. One tells you the next one, tells you the next one, a bit like induction, if you like. But this one you skip 2. It has to do with the nature of these trig derivatives here and that n minus 2. Okay, that's where it comes from. Okay. So, really quickly, I'd like you to see if you can use this recurrence relation to evaluate I4. Can you do it? What would you get at the end? Have a go. I'll give you a couple of minutes. It won't take you that long. Let's see what happens. Let's try it. Okay, now I've already provided the first line for you. Okay, so the question will tend to be phrased to you like this. Just evaluate that. Sometimes part 1 or part A might be, show that this is the recurrence relation for sine n to the x, sine to the n x, sorry. Okay, so once you do that, you can start using it. Okay, so there's my I2 because I've jumped down, there's my n minus 2. Right? So once I see that again, I use the recurrence relation again. That's the point of it being a recurrence relation. Right? So you've got this out the front, which has already been integrated. What's going to come next? What's going to be in here? Well, you look to this, and you're sticking in 2's instead of 4's, right? So you're going to get minus 1 on 2. This is going to be, how many signs am I going to have? Just the one. What's going to happen on the end here? You're going to have plus a half I naught. Does that look right? Yeah. Now, that might seem strange to you, okay? But just remember, we've defined I naught in a way that was convenient to us, right? Is our definition for I consistent with a value of n being 0? And the answer is, yes it is, right? Because this is the integral that I know, right? Remember the point of going through this process is you integrate by parts, until you get down to something you can just regularly integrate, right? And not integrate by parts. Well, I naught is just sine x to the power of naught. Which of course is just 1, right? And I think we can integrate that, okay? So at this point now, I'm going to get rid of all of my i's, which means I also need to include a constant integration. Okay? And I can tidy this thing up. I've got my cos sine cubed there. What am I going to have here? Actually, I can take that half out, can't I? Why don't I do that? That's 3/8. That'll give me one of these. And what's I naught? We said it was the integral of 1, right? Which is x plus my constant. Okay? And of course, I just need to tidy up my my coefficients. Okay? But does that look okay? Does that make sense? Now just pause and reflect on that for a second. Okay? Admittedly, this took some work. This took some serious work. Okay? But once we got to this, which you'll start to recognize, look at the number of lines from here to here, right? And in previous times, you would have looked at this and just said, insoluble. You can't do anything with that. It's to the power of 4. Are you crazy, right? But recurrence relation just sort of make mincemeat of this kind of problem, okay?